Welcome back. So in the video today we're just going to go through a project design from start to finish. One thing that's been lacking in a lot of the other videos is attention to wiring and routing and just sort of general design principles. So we're just going to go, I have kind of a small project that I need to put together, and we're just going to go through it start to finish, everything that's needed to sort of build sort of a small, this is going to be a preamplifier for a piezoelectric acoustic microphone. So we're going to just start with doing the schematic. We're going to get some parts from a vault, some parts from libraries, then do the board layout, and it all should go pretty quick. It's a fairly small, simple project, but I want to just show once again everything from start to finish. What we won't do is we won't actually export the Gerber files in this one. There's two other videos where we talk about how to take a project and export the Gerber files and drill files for fabrication. So we're going to skip that for this one just to save time, but we're going to go through sort of all the other design steps. So part of it's going to be, so first of all, I'm just creating a new project. Always does that to me. So first of all, we're just going to create a new project. So this is going to be, and again, in other videos we've talked about how to set up all these settings correctly. So we'll just call this Hydrophone Preamp. So again, this project is going to be, we have a piezoelectric microphone which is being used as a hydrophone, and the first thing we have to do, that signal from that hydrophone is very weak. The first thing we have to do is amplify it, and we also want to do a little bit of filtering to sort of only leave the frequencies of interest, but it is just a preamplifier, so the signal will go through later filtering stages. For right now, we just need to get a lot of amplification as close to the microphone as we can, and we need to maybe do a little bit of filtering just so we don't have too much noise that gets amplified early on. But we're not going to spend too much, we're not going to worry too much about the filtering. We're just going to do just sort of first order filters and just like a first order bandpass filter. Okay, so starting with the schematic design, I'm also not going to do the project titles and stuff just to save time here. So this project is for a, it's the hydrophone, and the microphone for it. I have the files for the microphone on a different computer, so that's fine. We won't put the microphone on right now. We'll do the design for everything except for the microphone. So let's start with the basic amplifier design. So I have just popped up here really quickly this diagram showing a just basic low pass and high pass filters. And so what we're going to do is we're going to build an amplifier with a gain of about 100. So that's a gain of about 40 dB. And we're going to have a first stage that does a gain of 10, a second stage that does a gain of 10. And the first stage we'll just do a low pass filter like this and a high pass filter like this. Now in this case we're going to be using the non-inverting amplifier configuration, which is what's shown here. These are non-inverting low pass and high pass filters. Usually people don't like to use non-inverting amplifiers for filter design because, of course, a non-inverting amplifier has a minimum gain of 1 always. So you can't actually attenuate a signal with a non-inverting amplifier. However, in our case, we have a very small signal. A couple of millivolts is the most we get out of this signal, and we're going to do a massive amplification on that. So even though we can't attenuate those frequencies outside of our range, the fact that we're amplifying this by a factor of 100 means that as long as we don't amplify those other signals, in effect we're basically sort of attenuating those, or at least we're sort of not amplifying them in our overall output signal. So we're going to basically produce these two circuits right here, and we want to have the reason we want to have a non-inverting amplifier design is because we want to have the input be connected to that positive terminal. There's two reasons for that. One, if we're using a JFET op amp, that input terminal has a very high input impedance. We want that so we don't have these piezoelectric microphones, these piezoelectric crystals that we use to pick up these vibrations in water. They can't handle a low impedance load. So the lower the impedance load, the more it's going to attenuate that signal. So we want to have a nice high impedance input to this amplifier design, and the best way to do that is to just have the input feed directly into the positive terminal of a JFET op amp. So that's what we're going to do. And so then we'll do another non-inverting high-pass stage for this. Okay, so the good thing is most amplifier ICs, most op amps, we get 2 per package for a standard 8-pin IC. And so we're just going to start our design with a basic JFET amplifier, 8-pin SOIC amplifier. We actually don't have to use this amplifier later on. The nice thing about most op amps, they use a standard footprint. We don't have to use this exact op amp that we're choosing later on, but we're going to use the footprint for sort of a basic LF353 JFET input, high band, relatively high bandwidth op amp. So let's go back and let's go to our vault to get that op amp. So we're going to start by searching for LF353, and I've looked for this before, so I know it's there. Now we're going to go, one thing we want to check is we want to make sure that we're getting the right thing we want, but this is going to have to be tiny, tiny, tiny. So we're going to start with a package that looks like this, or not like this. This is a through hole. We want something smaller, so we want, at the very least, a package that's a 8 SOIC, sort of a standard SOIC package. So this looks pretty good. Let's just check to make sure. And what we should do is get the exact one that we're thinking of, because even these SOIC packages, sometimes they have a width that changes. This looks like it's going to be good enough, so let's use this. So if I respond here, so we're going to place this component on our schematic. And one thing I'm going to do is, first of all, I look down in the bottom left corner and I see my grid is 1. So always pop that grid up to 10. So if we start with a grid that's nice and spacious now, it's going to help us later on. Okay, so let's put this guy about here-ish. And this guy we'll put... let's give ourselves some space. About here. Okay, so these are, so one thing you'll notice is that part just had a part A and B. So we have one physical device with 8 pins, but that device contains 2 symbolic parts. So in the schematic editing, we are looking at the symbolic representation of the functionality of the device. So if we have 2 functional devices in one package, a lot of times we'll show it as 2 functional system blocks in the schematic, even though ultimately it is one single package. So I just placed 2 parts, but it's going to correspond to one single chip on the board design. Okay, so let's everything looks good here. So let's make our standard design here. So I'm going to do I'm going to add a couple other things to this right now. We need this preamplifier is going to have a connection that gives it power, the power rails. So positive 9 or 12 volts, negative 9 or 12 volts ground. And it's also going to have a signal that is a pin that is the signal coming back. So the preamplified signal coming back. So let's add a header just to make it easy on ourselves. So let's go to library. Let's go to miscellaneous connectors. Oops. So we needed 4 pins for that. So positive, negative, ground reference, and signal. So we'll just plop down a 4-pin header for that. Oops. And we can put that guy wherever. And now let's do a 2-pin header. For now, we'll do a 2-pin header to represent the connection of that acoustic microphone. I do have a footprint for the acoustic microphone. I just forgot that it's on a local library on a different computer of mine. So let's hit escape, go back to the libraries, do a header 2, place header 2. Okay. So the first thing I want to do is I want to label these header pins. So usually for labeling these, because the orientation is this way, I'll give these guys a little bit of a lead here, a little bit of a wire lead. And so I'm just hitting escape after placing each wire. Now I'm going to go through and put net labels on these. And so this is going to be our input to our from our microphone. So we'll just call this mic positive mic terminal and negative one. So with these piezoelectric microphones, there actually isn't really a difference between the positive and negative terminals. Not really. Ultimately, it's just two sides of a piezoelectric crystal. But you know, we gotta call one and one the other. So plus and minus is as good as any as a way to differentiate one side versus another. So and then for this header, you know, I like to do my power and grounds on the outside. And actually, for the power and grounds on the outside, I don't need a net label. Oops. So I can actually just do a power and ground. Oops, I didn't want to do that actually. Well, that's fine. We'll do another power connector here. And extend that wire over. Oops. Okay, so VCC doesn't have any meaning here. In this case, we have a differential power, so we're going to have positive 12, negative 12. So what we can do is we can actually change the names of these power nets. So we can just call this guy plus 12, or yeah. And we can call this guy minus 12V. So plus minus 12V. This guy is going to be this will be our sig out. So coming into this, we have ground, our plus and minus power rails. All three of these signals should be fairly stable, so they shouldn't be wiggling. So they shouldn't actually be causing capacitive or inductive interference with this sig out, but usually we still want to keep the grounds near the outside. It's good to keep the ground near the outside. At least it gives you an option to shield with it, depending on the type of connector that you're using. But then we'll keep our signal in the middle here somewhere. Probably for this application we didn't have to do it that way. It's just kind of a choice. So now we got our signals. So now we are going to start doing our design here. I'm going to try to do everything with 0603 components. But for right now, the first thing we can do is power these op amps. So we can place some power rails on these guys. Okay, and I just named all these power rails the same as I had here. So now we're going to go, so for the standard, so we're going to start with a low pass gain of 10 stage. So we will go again to our libraries. We're going to have to place some resistors now. Miscellaneous devices. My 0603 resistor is going to be a res 3. Make sure that 0603 package is selected. Now we want to be careful because we might not want 0603. In particular, we probably want these resistors to be stable, to be thermally stable. If these are going to go inside of water for an acoustic microphone, we don't want the resistance when it cools shifting a lot and changing the frequency of these filters. So we might want to check and make sure that there's an availability of a resistor that has the proper sort of temperature coefficient that we're looking for in this package. For right now, I'm just going to assume that's all been done. I don't want to go through that process of searching for it and waste everybody's time. So we're actually going to place a bunch of these resistors. So the first thing is, I said we want a really high impedance input, but we do need to keep the input to the positive terminal somewhat connected to our ground reference. So if we this is a JFET op amp, it has an input impedance of like typically giga-ohms, if not more. So it is possible to have a slow accumulation of charge that can increase the voltage of that terminal, which can eventually cause our signal to clip. We don't want that. So we do want to keep that tied, loosely to to our ground reference, so we do have to put a fairly large, a few mega ohm resistor there at that positive terminal to cause that. We're going to have a resistor here. We're going to have a resistor here. And I can already tell I put this guy in the wrong spot. I didn't give enough space. So let's just drop a couple resistors here and here. We'll call that good. So let's move this guy over here. Oops, look what I just did. Okay. Actually, keep forgetting what I'm gonna have to do for this guy. Okay. So we can start by plugging in some, just to make this thing clear, we can start plugging in values here. This guy we're going to make about 2 mega ohms. This guy, 1K is probably okay for that. And this one can be 10K. So again, we're going to do a gain of 10 on this stage, so that'll do that, and then we're going to do another gain of 10 for this stage. So the overall, we're going to have 40 dB of gain for this amplifier. So 1K, 10K, that should be fine for that. Now, this particular op-amp that we're using, the gain bandwidth product is 4 megahertz. So with a gain of 10, we're going to be able to go up to a frequency of 400 kilohertz, which is plenty. That's plenty for us. I mean, that's good. We're operating in about a 40 kilohertz range, so we're not too close to that gain bandwidth limitation there. Okay, so 10 and 1 to give that an overall gain of 10. And then we'll do it again. So we'll have 1 and 10. And again, we're going to have all of these guys are going to, we're going to add capacitors in here to filter this for both of these to create the low pass and high pass filter. We also want to tie this guy to our ground reference, so I want to make sure this guy is tied to our ground reference. We want to make sure this guy is tied to our ground reference, and we're going to want to make sure this is tied to our ground reference. Now we're going to go to the capacitors, go back to libraries. So our standard ceramic 0603 capacitor is going to be a cap semi. And again, we might not want ceramic capacitors. You know, ceramic capacitors have bad temperature coefficients. They have, you know, they're not great. So we might want film caps for this application. We really might want film caps for this application. They're kind of big, though, and they're kind of expensive. So for now, we'll just stick with 0603. Place that guy. So we got to place one here in parallel with this resistor, and it's getting a little crowded. So one here and one in series over here. Okay. So this, you know, really usually the way I think about capacitors is capacitors are basically a very high resistance to very low frequencies, and they're very low resistance to very high frequencies. So in this case, this is a low pass filter. This capacitor becomes a very small resistance to high frequencies, and so your capacitor ratio drops precipitously for higher frequencies. And here the opposite is true. Here the gain ratio is this resistance divided by this resistance, and effectively, I mean, of course, this is not a substitute for a circuit analysis class, but if you think about the impedance of a capacitor like just a resistor that's a function that has a resistance that's a function of frequency, this capacitor at very low frequencies, this capacitor becomes a high resistance, which increases this resistance here, which decreases the overall gain of this for low frequencies. So in this case, our gain is decreased for high frequencies here, our gain is decreased for low frequencies over here. So that's how we get our low pass, high pass combination here. So we could put values in here. I'm tempted not to. For right now, I haven't actually done the calculations, but it's basically going to be this. The cutoff frequency here using these filters is going to be, 1 over 2 pi RC. And so for now, we'll we're not going to do that calculation right now. So let's wire this guy up. What am I doing here? So in this output here, oops, that wasn't quite done. So this input here is going to be our mic positive here. So this input here, we can just label that. And then in this case, we'd want our mic negative to be connected to ground. Okay, so is that weird to connect it ground and mic negative? We'll see, but sometimes what you do is you'd have a separate circuit over here just showing that it's tied to ground. We'll see. Okay, so this guy is our output though, so this has to be... So just really quickly here, let's look at this, give it one last look. Everything looks okay. So again, these values are listed. These are not correct capacitor values. Sometimes it's good to add a note here too. So we could just add a text string, and we could say something like that, and then maybe place a little line here too. Just have a little indicator. It's kind of sloppy, but something that just says, okay, you can choose that frequency based on these calculations. So, and then we can do that later on. So, okay, let's annotate this thing. Okay, and just we should check this thing. I'm just going to go directly to updating the PCB. It'll throw a fit if it had a problem, but I'm trying to move a little quick here. Okay, so everything fine, and okay, so we're going to move all of our parts onto the board. Right now, let's just set a grid at, let's do 10 mil. So I always like to, when first laying these things out, I like to go back to my schematic here and see. So after the annotation, we had R1 up here, R3 here, R5 here. So we just know sort of where to keep these relative to that amplifier. The air wires will show that too, but you know. Okay, so another thing that's really going to be critical here is we want to keep that input microphone is a very small signal, very high impedance, very tiny signal. It's very susceptible to noise. So we really want to keep that microphone as close as possible to the op amp, to this amplifier. So really as close as we can get to this op amp, those is input pins. We want to avoid having long wires running, because the longer those wires are, the more they're going to be able to pick up noise, and the more that's going to, any noise that interferes with that signal before it hits the preamplifier, all that noise gets amplified. So minimizing that noise, we really just got to kind of keep the space limited. Looks like there's a pretty easy way to do it here. We can put that right here. And I don't like that designator being there, but okay, so it looks like we can kind of put that guy right here. And that's perfect. Look at that. We're going to be able to keep this really close to these inputs. So looks pretty good. Okay, so then we had, so if we go back here, we had R3. Let's do R3 now. And again, what's most critical is that initial stage of the amplifier is most critical. The second stage is the next critical after that. And any noise we get after that is going to be the next critical thing. So R3. R3 is here-ish. R1. That C1, we can do that next. Then we'll do, oh, we gotta get that R5 in there. And we'll do R4. C2. So and I'm it's hard to see, but I'm kind of, you know, watching these air wires rotating, and I'm also trying to keep balance between the alignment over here and the alignment over here, just to keep everything looking pretty. And then our last thing is R2, which is that feedback. Actually, it looks like you may want to move that guy to the inside. Okay. These guys around a little bit. Add a little extra balance here. Looks pretty good. Okay. Now I've got a lot of parts up high. I kind of want to keep this kind of compact around a small area. I might actually even move all of these guys down like this. Pull them in tight. Move these guys down like this. Pull them in a little tighter. Okay, and then this header, for reasons I'm not fully explaining now, I kind of want this header down here. Okay. Okay, so looking okay. Let's route this guy now. It looks like that's about as good as we're gonna get. Yeah, looks like that's about as good as we're gonna get. So, yeah, let's start routing, and we're gonna start at the most critical areas here. I don't like these default names. They're just large and obnoxious. Some people say the same thing about me, though. So, okay, let's start routing this guy. Start at the top layer. So this has got to be. Might as well make them bigger if we can. So let's start with 14. I think we could probably do this whole thing with 14 mil traces here. So this is the ground. Probably at the end I'm going to do a ground plane, so we probably don't even have to worry about this right now. Actually, you know what? I'm not going to worry about this right now. Let's leave our grounds unrouted. So this microphone, this one is critical. So we want to So I'm thinking actually I want to switch the order of these two. Yeah, so I'm going to hook that guy up. This one here. And this one here. That looks a lot better. So I'm routing all in the top layer. We haven't needed to pop down below yet, so might as well. Okay. So again, that's all ground. Let's route these plus and minus 12s. These definitely are important. So for the minus 12, oops. Sometimes you'll route something and you realize you're going to regret it later. It's kind of one thing I just did there. Probably going to end up undoing that. You can kind of feel it. This 12, boy, we got a lot of nests over here, so we're going to have to go around the other side. We're going to have to go around these, and I hate doing this because when we route around stuff like this, that routing is what defines the overall outer shape of our board. And I also, if I want to cut this close, when this board gets cut, if I want to sort of keep the board as close as possible, that means that that blade that's cutting the board, if it's off a little bit, it's going to be cutting this signal, which I hate to. I don't mind if it does it to a ground plane, but I don't like if it does it to a signal like this. So we might sort of come back and add stuff to that there. So our signal now, let's route this guy. And again, I'm sticking, I don't necessarily have to, but I'm sticking to the top layer. I promise I will eventually do a design that's complex enough to need more layers, but or to need to do a lot of routing on the bottom, but it doesn't look like we needed that much here. Okay. It's advantageous here. Oh jeez, look at that. Sometimes life just works out perfect. I still might be a little uneasy with that because, you know, sometimes if you're, so fabs say they can do certain processes, but if you're cutting it that close unnecessarily, sometimes these you'll sort of have a solder mask that's a little bit off, and then you can possibly get this little copper edge to bridge the solder. So it's probably okay here, but sometimes I'd worry about that and maybe drop that down a couple mils. Maybe drop it down a couple mils. Look what I've done here. Look at that. We may get to use the bottom after all. So first of all, let's see if that signal is critical. Net C2, I think that's the yeah, that's the negative input terminal to the second op amp on that board. Well, it's not the end of the world. There actually is a way I can avoid it too. You know what? Let's route on the bottom. I can avoid it. I could switch these two and route it through here and avoid it, but let's show routing on the bottom because we haven't done a lot of examples of that. So if we want to route this signal, if we want to get this to the other side, what we can do is we can, I like to take the signal out there, and if you hit the plus key will change while you're routing. The plus key will switch layers, and switching layers, it knows you have to put down a via there. So if this via, we didn't set our defaults, we didn't set our rules down to the proper rules, so we're going to do 13 mil hole, 27 mil diameter. Okay, so we're going to plop that there, place it wherever is good. I like to keep them, especially when we're on the underside of a chip like this, you can't see if you get a solder bridge to these things. So I don't like to put, some people put them here, you know, some people put them like absolutely as close to the pins as the software will let them. They'll do something like that. I hate to do stuff like that because if we get a little solder bridge from the other pin in there, we're never going to see it. So I usually like to give it a little bit of space if it's underneath, away from those pins. And then we'll route this. So we'll route this to here-ish, and then we can press plus again, and it'll switch us back to the top layer. We can connect those nets. So not ideal, probably better ways to do it, but that gets it. That's routing on the bottom layer. So routing on the bottom layer, typically what I do is I hit the plus key. That's the plus key on the numeric keypad. it'll switch layers and tell you and have you place a via. Place the via, route on the other layer, then press the plus key again to switch back to the other side of the board. And we route it that way. Okay. Okay, so looks like we have everything routed now. You know, we had to do that guy. We have everything routed now, and this is not the prettiest I've ever done, but whatever, it gets the job done. Now we're going to do the fill for this board. So now we're going to do a fill here. Okay, so we will do, and we're going to fill it with the mic negative, which is sort of our ground reference. And that should sort of give us a good ground connection here, but we'll take a look at it and see how it looks. So place polygon pour. So I think we did label it ground, but it seemed to show mic negative, so that's fine. Oops, yeah, we'll call it ground. And still connected to that mic negative net. For overall, same net objects, remove dead copper. All looks good. Okay. So I'm going to set my grid a little bit coarser now, maybe do 100 mil. Nah, not that coarse, 50 mil. Okay, and what I'm going to do is, so right now we have sort of our style for sort of defining this polygon. If you press spacebar, it changes the sort of side that it bends the corner at. If you do shift space, it changes the type of corner. So in this case, I like this one, the rounded corner, but let's do a really rounded corner. So what we can do is, if we press the period key, so it's the period key or the greater than symbol here, you can see down at the bottom that radius value is changing there. So we can have that radius value change to whatever we like. Let's do a nice clean 300 mil. Looks pretty good. Oops, and our layer is the wrong, oh no, that's the right layer, that's fine. We'll leave some space here. Look at that. Okay, so let's double check. Let's make sure we actually got a good route here. So this is our incoming ground. That does connect pretty well to here. Doesn't really get a good connection to here though. Look at that, right? We don't have all this ground connection here, just runs through this thin little tiny strip here. That's not a good ground, even though we did a ground pour. That's not a great ground. So let's give ourselves an even better ground here. Let's give ourselves a better ground by sort of redoing that ground pour, but on the other side now. So we'll do place another polygon pour. And now we could also reconfigure everything to get a better ground, but so we'll do another one. Follow that same. Oh, okay. Now we got a good connection, right? So now we have these two through holes are tied together through that bottom ground pour. If we switch back to the top layer, that gives us a nice solid ground connection to here. This, I feel much better about this ground connection now. So there are other options. There are other things we could have done to sort of expand this out and get a better connection just through the pour, but doing it on both sides should be fine. So now let's move around some of these annotations here. That's not great. Definitely need a grid that's finer than that, though. And so a lot of times you're not actually going to get them to fit perfect. And in this case, we're not even going to get them to fit. Sometimes what I'll do then is I'll change it to, some tinier. P2, I don't even want P2. What I want is just a polarity indicator. So put that there so we know that's the positive side. Move over R5. Okay, and really what we should do is make sure that just for cleanliness that all of these are the same size. We can do that kind of right away. We can just click one and right click it and do find similar objects. Make sure its text is the same. Let's do text height because we'd already changed some. Make sure this is the same. So that's going to choose all the text on here. This is the find similar objects window. It's going to find all the text that is the same height. We're going to click OK, and then it brings up the PCB inspector where we can change this. So we can change all of these immediately to 40 mil height and 6 mil width. And that's about the minimum we're going to be able to get away with this fab. So now we can and actually here, probably for this one, we can just take this guy's designator and just use it for that's not going to fit. It ain't pretty. It ain't pretty. Pretty ugly, actually. We should probably clean that up. Don't want to, though. Not enough time. Trying to keep this video under an hour.